Let us begin with the Laplace transform for periodic functions. So let me define what is a periodic function. A function ft for t greater than equal to 0 is said to be periodic of period t greater than 0 if f of t plus capital T is equal to ft for all t greater than equal to 0. So of course we already know some examples of periodic functions. One is the sine function. This is periodic with period 2 pi. So this is 2 pi here, and our function is ft equal to sine t. Similarly, ft equal to cos t has period 2 pi. So now we would like to compute the Laplace transform of a periodic function. So the theorem is that if f t is periodic with period t for some t greater than 0, then the Laplace transform of ft is equal to 1 over 1 minus e to the minus st multiplied by the integral. So this is in the numerator, integral from 0 to t ft exponential minus st dt. Note that this is the Laplace transform of the modified function f tilde t, where f tilde t is equal to ft for 0 less than equal to t less than capital T, and 0 for t greater than t. So this is the truncated version of f, and if you take the Laplace transform of f tilde t, you will get 0 outside t greater than capital T. So you will only end up with this integral from 0 to t. So this says that the Laplace transform of the periodic function f is 1 over 1 minus e to the power minus st times the Laplace transform of the truncated function f tilde t, and this is valid for s greater than 0. Note that we did not assume that f is of exponential order here in this theorem. So let's try to prove this. So let fs denote the Laplace transform of ft. So then we can define the integral 0 to infinity ft. So now we are going to break up this integral from 0 to t. The first integral is from 0 to t, and the second integral is from t to infinity. So again, this first one exists as a Riemann integral, assuming ft is piecewise continuous, and this one exists as a improper Riemann integral. So now I can make the change for the second one. So in the second term we make the change of variables u equals t minus capital T. So of course du is again dt, and u goes from 0 to infinity now. So this equals 0 to t ft to the power minus st dt plus 0 to infinity f of u plus t exponential minus s u plus t capital T du. So we can take out this term exponential minus s capital T outside the integral sign, and you are left with f of u plus t exponential minus su du, but we know that f is periodic, so this is equal to fu. Therefore, we get that this is equal to 0 to t ft exponential minus st dt plus exponential minus s capital T, and we have the Laplace transform of ft again. So our left hand side was also the Laplace transform of ft. So assuming that this is finite, so assuming that LFT exists, this implies that the Laplace transform of ft is simply 0 to t ft exponential minus st dt divided by 1 minus e to the power minus st, valid for s greater than 0. So we have shown that the Laplace transform of ft is of this form. So let's look at an example. So I will draw a graph for a function. So this is our coordinate plane, this is the t axis, and this is ft. So well, ft I have yet to draw. So our graph of ft will look something like this. So we fix a positive number a, and we can divide our t axis into multiples of a. etc. So the graph of ft, this is 0 from 0 to a, so this is 0, and then this is 1, so this value is 1, from a to 2a, so from a to 2a this is 1, then again from 2a to 3a it is 0, and then again from 3a to 4a it is 1. This is 1 again, and so on. It is defined for all these intervals a and ka and k plus 1a over the real line. So this ft, f of t, can be written as follows. So this is 0 if 2ka less than or equal to t less than or equal to 2k plus 1a. This is for k equal to 0, 1, 2, etc. and 1 if 2k plus 1a is less than or equal to t less than or equal to 2k plus 2 times k plus 1 a. So again k equal to, here k is equal to 0, 1, 2, etc. So this describes our function ft, and this function is called the square wave function, and this is very important in engineering subjects, like in electrical engineering for example. This occurs quite frequently. So let us compute the Laplace transform of ft. So by our formula for periodic functions, so now note that the period here is 2a. So at every 2a the function repeats its behavior after every period of length 2a. So our period is 2a. So therefore the Laplace transform of f of t is the integral from 0 to 2a ft e to the power minus st dt over 1 minus e to the power minus 2a times s. Now note that from 0 to a ft is 0, so this is nothing but 1 over 1 minus e to the power minus 2as, and the integral is from a to 2a of e to the power minus st dt, because in this region ft is equal to 1. Therefore you get 1 over 1 minus e to the power minus 2as, and then e to the power minus st over minus s, a to 2a, and this is nothing but 1 over 1 minus e to the power minus 2as times s, and on the numerator you have e to the power minus as minus e to the power minus 2as, and this is valid for s greater than 0. And now you can simplify a little bit further. Let's see. So this is equal to 1 over s times 1 minus e to the power minus 2as, and then you can take out one of the e to the power minus as, so you will get 1 minus e to the power minus as here, and here in the denominator this is of the form a square minus b square, where a is equal to, well, not the same a, let's say alpha square minus beta square, this is equal to 1, and beta equal to e to the power minus as. So therefore we will get 1 minus e to the power minus as by s 1 minus e to the power minus as 1 plus e to the power minus s, and one of these factors cancels out, and you can rewrite this as 1 over s times 1 plus e to the power as, and this is valid for s greater than 0. So this is a an application of our formula for periodic functions. Let's look at another periodic function ft. This is modulus of sine omega t for t greater than or equal to. So the graph of this function looks something like this. So you have 0, pi by omega, and then 2 pi by omega, and so on, and the sine function from 0 to pi by omega is positive, but from pi by omega to 2 pi by omega you take the modulus sign, so it's again positive, and it repeats like this in the entire interval 0 to infinity. This function has a special name. This is called full wave rectified sine function, and this is also important in engineering problems. So let us try to compute the Laplace transform of f of t. Here note that the period is simply pi by omega. So by the formula for our periodic function we get the integral over 0 to pi by omega e to the power minus st sine omega t dt over 1 minus e to the power minus pi by omega times s. Now if you compute the integral in the numerator, you will get omega over s square plus omega square multiplied by 1 plus e to the power minus pi over omega times s, and you have 1 minus e to the power minus pi over pi over omega times s in the denominator, and this is your solution for s greater than 0. Now let us come to the next topic, which is the Laplace transform for integrals. We have already seen it, the Laplace transform formula for derivatives. Now this we can also compute it for integrals. So this is our theorem for integrals. So suppose that ft is piecewise continuous and on 0 infinity and of exponential order alpha. So remember that this means that the mod of ft is less than or equal to m e to the power alpha t for some t greater than or equal to t naught, for all t greater than or equal to t naught. Then the Laplace transform of the function 0 to t fu du. So this is the integral of f for the range 0 to t. This is nothing but the Laplace transform of ft divided by s, and this is valid for s greater than alpha. So let's see the proof. So the Laplace transform of 0 to t fu du, we have to compute this. So note that this the derivative, so let me call this gt. So the derivative of gt is simply f of t. So we can use the derivative formula. So from the derivative formula, we have that the Laplace transform of ft is equal to s times the Laplace transform of gt minus g of 0. But since g is defined as an integral, this is simply 0, and so we are left with L of ft is equal to s times L of gt, and this formula is valid for s greater than alpha. This is needed for the Laplace transform of ft to exist. This implies that the Laplace transform of gt is simply 1 over s Laplace transform of ft, and this is our theorem. So the proof is really easy, and it follows from the derivative theorem, and we have already seen one example here. So if you take the ft to be integral 0 to t sine u over u du. So we have seen that the Laplace transform of ft is equal to 1 over s times the tan inverse of 1 over s, and this was nothing but the Laplace transform of sine t over t, valid for s greater than 0. So again we can verify this formula for the Laplace transform of integral 0 to t sine of u over sine u by u du. Now let's look at a more complicated example. This is integral 0 to t u log to the base e ln u du. Now this function, let me call it gt, this function defined by t ln t is a piecewise continuous function on 0 infinity, because so if t is greater than 0 there is no problem, so it's continuous at all points t greater than 0, continuous at all points t greater than 0, and the limit as t tends to 0 plus gt is simply 0. So this is easy to show. So let's see the limit as t tends to 0 plus t ln t, and if I take y to be log of t, then as t goes to 0 plus, y goes to minus infinity. So we can write it as the limit as y goes to minus infinity, e to the power y multiplied by y, and this is the same as the limit as x goes to plus infinity. So I am again changing x, again changing the variable from y to x. So this is nothing but x times e to the power minus x, and we know very well that this is 0. One can evaluate it, for example, using L'Hopital rule. So we see that this is 0, and so gt is piecewise continuous on 0 infinity. Now we have to compute the Laplace transform of 0 to t u ln u du, and this is nothing but the 1 over s times the Laplace transform of t ln t. So we haven't seen yet the Laplace transform of this function, so let's try to compute it. Note that there is a multiplication by t, so this is nothing but 1 over s minus 1 times the derivative d over ds of the Laplace transform of log t. So let's compute the Laplace transform of log t. This is nothing but 0 to infinity ln t e to the power minus t st dt. Now note that this Laplace transform exists because of our sufficient condition for function which is not piecewise continuous at t equal to 0 to exist, which was that t to the power alpha ft limit as t goes to 0 plus, this should be 0 for any alpha between 0 and 1. So one can compute this for ln t, and one can show that this is in fact 0 for any alpha between 0 and 1. So this exists. So this Laplace transform exists for s positive. Now to compute it, let's make a change of variables. This is equal to, so I am making a change of variables u equal to st. So du is s dt, and since s is positive, u also goes from 0 to infinity. So we will get the integral from 0 to infinity ln of u by s e to the power minus u, and then you have du over s. So 1 over s comes out, and you can write this as ln u minus ln s. So this is integral 0 to infinity ln u e to the power minus u du minus 0 to infinity ln s e to the power minus u du. Now this is a constant. We have seen that this kind of integral exists. We proved it for any s greater than 0 using our sufficient condition. So in particular for s equal to 1, we get this integral s equal to 1, and so this integral is finite, and this is usually called the Euler, the value of this integral is called the Euler-Mascheroni constant and denoted by gamma. So this is a constant you call the Euler-Mascheroni constant and usually denoted by gamma. Now the second integral is easy, second term is easy to compute. So this is equal to 1 over s gamma minus ln s integral 0 to infinity e to the power minus u du, but this is nothing but 1. So one gets 1 over s gamma minus ln s. So now we go back to our original function. So this was what we wanted to compute. So we have already computed the Laplace transform of ln t, and we have to take the derivative, and there is a minus 1 over s sign. So let's compute the derivative of 1 over s gamma minus ln s. This is equal to minus gamma over s squared minus ln s minus ln s over s squared plus 1 over s squared. So this is minus gamma minus 1 minus ln s over s squared, and so the Laplace transform of 0 to t u ln u du is equal to minus 1 over s times this whole thing. So this is minus gamma minus 1 minus ln s over s squared. So one can simplify if you like, and you will get gamma plus 1 minus ln s over s cube valid for s greater than 0.